Well, hello there.
Hi there.
Hello.
You're
I'm
in the
very-
dark,
I
Richard.
am. I'm having difficulties with my
Whoa, here
with
we
my
are.
laptop camera tonight. So for some reason, it really doesn't want to show anybody what I look like, which is probably
maybe I can help
to
you.
it's to everyone's benefit.
Well,
try to help you there.
It looks like a noir image, a little
Yeah.
on the black and
Yeah.
white side.
Yeah, this is
Yeah.
better. This is better. I
Yeah.
can live with this. Well, how's everyone tonight?
Yeah, we're good.
Doing
We're
good. Yeah.
It's nice weather up here. We got clear skies, no smoke,
Warm.
warm. Only problem is
We have loud.
we have a party going on outside. So,
It's loud music.
yep.
And
We
some
may
loud
yet-
people too.
And as I said earlier, we may yet hear the chicken dance tonight.
Right.
So before we get started, I want to remind everyone who we are and some announcements. I'm Rich Ozer, and we have John Curry and Rick Taft and Gerald McKeegan, and we are sitting right next to Nellie, our 36-inch research reflecting telescope. You could see Nellie protruding from my head a little bit right here, and we do this every Saturday night. It's called Virtual Telescope. And what we do is we attach a camera to our 36-inch reflector, and we try to show you some stuff. We've been doing this now for a long time, right? It's almost 2 years.
Since May of 2020. Yep.
Yeah.
So
Good God.
year and a half.
Year and a half.
Yep.
The
Still
reason
don't know
we're
how to
doing
do
this,
it
of
either.
course. Yeah. We have no idea. We have no idea what we're doing.
But we're still practicing. We'll get there someday.
Yeah.
And of course, the reason we're doing this is that the Chabot Space and Science Center is still closed to the public, although we are planning and moving forward for a reopening in November. So it's coming up pretty soon. And in the meantime, though, we rely on your contributions and donations. And if you're on Facebook, you'll notice that there is a donate button. And if you guys are able, please donate to our science center. I'd also like to thank Fremont Bank, who is a community supporter and helps us put on this program and others. So hands clap for Fremont Bank. I guess that's it. Then we're going to get started with Alberio, I think, right?
Okay.
Yeah.
Well, we're ready to rock and roll here, so to speak. Let me.
So
That's outside.
So
It's going downhill already. I'm sorry.
That is
So
right.
we have a camera on the telescope, and it's being run by Rick Taft here. So bear with us for just a second while we get an image up. We are starting with the double star called Alberio, I think. How we doing there, Rick?
We are. Actually, I'm looking at it right now. What's
Yeah,
it
but
showing?
your
We're not
screen-
seeing it though.
We're
Yeah,
not
but you're-
seeing it.
It says Rick has started screen sharing, but he hasn't finished yet.
I lost the connection again. Okay. Let's try this one more time, shall we?
Okay.
All right. So that.
There we go.
Eureka!
All right.
Woohoo!
Hey, there we go. So for those of you who are Cal Berkeley fans, this is often called the Cal Star. Cal Berkeley's colors are blue and gold, and these two stars are blue and gold. We call this Alberio. To the naked eye, it looks like just one star. Hence, it has only one name. But when you put a telescope on it, you see that there are actually two stars there, one blue and one gold. The two stars are pretty close together. After much debate, I think it's pretty well been settled that the two stars are not orbiting around each other. There has been
If they were, the period would be at least 75,000 years.
yeah.
So
yeah.
it's probably not. It's probably not the case.
Right. So these two stars are along the same line of sight, but they are not orbiting around each other. I've been doing a lot of research here over the last couple of weeks about this, and depending on which paper you read, the separation is anywhere between 4 and 40 light years. So take your pick. But star colors tell us a lot about the temperature of stars. So you see a star that's bluish and a star that's gold in color. And that tells us that the blue star is the hot star. It's a young main sequence star, relatively young main sequence star, has more mass than our sun. Because it has more mass than our sun, it is burnt or fusing hydrogen at its core more profusely, and that makes it hotter. So it appears bluish in color. The gold star, on the other hand, is a star that's actually a little bit later in its life. It has started to swell up. As stars get old, they swell up. Their outer surfaces start getting cooler. And as the surface gets cooler, the color changes and becomes that kind of golden yellow color. As the star continues to expand, the color will become a deeper golden. Eventually it'll be orange, and when it gets really big, it'll be almost reddish in color. So this is how astronomers tell the temperature of stars. And we combine the temperature with other data, the distance and so forth, and we're able to estimate the size and age of the star as well. So we know that the gold star is a star that has swelled up. It's now much larger than it was originally when it was a main sequence star, giving it that gold color. Like I say, there's been a lot of debate about whether these two stars were orbiting each other. As recently as 2 years ago, I was talking to one of the prominent astronomers at Cal Berkeley, Alex Filipenko, and he was still not convinced that this was 2 years ago. But there's been some more recent papers that sort of have concluded pretty conclusively that they are, in fact, two separate stars, several light years away from each other. So they're not orbiting each other.
Gerald, which one is closer to us?
Good question. If you'd asked me 6 months ago, I would have told you the blue one was the closer of the two stars. But I was just reading a paper a couple of days ago that they think maybe that it's actually the other way around, that the gold star is the closer of the two stars.
Oh.
So,
Well, this is the fun thing about science.
yeah.
It's like everything can change because of new evidence, and it only resolves itself once you get enough data to make something completely conclusive.
Yep.
And things like stellar distances and orbital periods and those types of data sets are very, very hard to come by for very distant objects.
So anyway, this is Alberio. One of the cool things about Alberio, it's a naked eye object, although here in the Bay Area, it's a bit of a challenge to see it naked eye, but you can see it naked eye here in the Bay Area. But if you put a pair of binoculars on it, not only can you see it easily, but you can actually see this a double star, even with a pair of binoculars. So you don't need really high magnification to see that there are two of them there. All right.
Yeah.
So we thought that'd be interesting. Now, you'll hear astronomers talking a lot about double stars. And although these two are probably not orbiting around each other, probably half the stars that you see with your naked eye are actually binary star systems, two stars that are in fact orbiting around each other. Turns out that binary systems and sometimes even trinary systems or even more complex systems are quite common. We don't notice them with our naked eye because they're so far away, but when we look with telescopes, we see a lot of double stars out there. When they're separated like this, we say they're a visual binary. But a lot of times, two stars that are orbiting around each other, they're so close together that even with a telescope, we can't see two stars. We see them only as one star. But there is a technique we use where we put a spectrometer on the telescope and look at the spectrum of the stars. And if there's a binary system where the two stars are orbiting around each other, if they're too close for us to see, what we may see with a spectrometer is two spectra that are almost overlapping, but moving back and forth to each other. I'll see if I can get this. So if you imagine the absorption line in the spectrum of one star is slightly offset to the absorption line of the other star, and they move back and forth to each other. That tells us that we have two stars there that are orbiting each other, and we call that a spectroscopic binary system. So we learn a lot from binary star systems. Once we are able to confirm that there are actually two stars there, quite often we can use the period of the two stars. If we can calculate the distance to the stars, we can actually determine the mass of the stars. Even if we don't know the distance, we can determine the mass ratio of the two stars. Because as you can imagine, if there are two stars and one is a lot more massive than the other, instead of going around each other like this, they go around each other like this. So one star is only moving a little bit and the other star is moving a lot. And the ratio of the difference between the motions of the two stars is directly related to the ratio of their masses. So we learn a lot from looking at binary stars. But like I say, this particular one, it's a double star, what we call an optical double, because they are in line with each other, but they are not actually orbiting each other.
Hey, Renato has a great question. What do we call each of the two stars in a binary system?
A and
Usually,
B.
right.
Yeah, alpha and beta. So if you were to look up these stars in one of the many star catalogs out there, you would look them up as alpha Alberio and beta Alberio.
Yeah. Normally, if they have a name, it's just a single name because you can't see them naked eye as two different stars.
Yeah. Now, I also read a paper that suggests the possibility that the gold one is, in fact, a spectroscopic binary. So there may actually be a third star in this image, but it's so close to the gold star that we can't see it.
Let me guess. Its name is C.
You got it. You got it. You got it. So anyway, pretty interesting. And this is like I say, this is how we learn a lot about stars, is by looking at binary stars. All right. So our next target, I think we agreed was going to be M15.
Yeah.
All right. Well, let's go there. Rick, I'm not sure if you're going to be able to see it in live view.
Okay.
But leave it on live view. I'm going to go to
Okay.
an intermediate star so we can make sure we got everything lined up here.
Okay.
Stand by here. Actually, it's a star that's a little bit past it, but it's a nice bright star called Enif. And we're going to see if we can see enough of Enif.
Enif is in Pegasus. It's
Yeah. It's on the
out
nose.
on one of the legs.
I think we found it.
I think you found it. Yes.
Yeah.
Okay.
Okay, all right, let's get it centered up here. Hang on just a second.
Here, let me get a crosshair for you there.
I think I found it. Whoops, overshot. Okay. All right, so this is Enif, and you notice it too has a gold color, which tells us it's on the cool side as far as star temperature is concerned. And now we are going to go to M15, a globular star cluster not too far away from Enif. It's actually very far away from Enif, but on the plane of sky, it's not too far away. And you can actually
there it is.
catch a
Okay.
little bit of it
Alright.
right there. Maybe do like a 15-second exposure.
Yeah, that looks good right there. Let me let's go to imaging and let me switch this up, change the name to M15, 15-second exposure. All righty, let's see what
15
happens.
for 15.
Yeah, 15 for 15. All right.
So while he's doing that, let me tell you about this. This is called a globular star cluster. Globular star clusters are like balls of stars out in space. This one has about 450,000 stars in it, and it is about 33,600 light years away.
Okay, we need to focus this.
Yeah, we certainly do.
Let us go. So focus has changed.
Yeah, let's go to a nearby star.
All right, so let me go back here. And now all of a sudden I don't have control to go back. Richard.
You don't have what?
I cannot get back to
Live view.
focus. Live view, yeah.
Yeah.
All right, technical difficulties.
You could do a disconnect and then reconnect and see if that clears it.
Actually, everything is grayed out on that. That's really weird, isn't it?
Yeah.
Hey, what's going?
Oh, you know what? It's shooting. That's why.
Yeah,
Hit the abort button in the upper right corner.
Oh, okay. Wait. Why was it doing that? Well, this thing has a mind of its own.
You might have it on loop.
There you go.
Yeah, okay.
Yeah, there you go.
All right, now all right, let's go back. Frame and focus.
Oh, there you go. Good.
Okay, there's
Phew.
a star. Good. All right, let me bring this up.
That's actually the cluster still, so.
No,
the one he's looking at right there is.
Oh, I see what you're doing. You're going to move
Yeah.
it to the lower left. Great.
Find the.
You want me to move it to it's centered?
No, this is fine. It doesn't have to be centered.
Yeah, but it might help if it was.
No, it's okay.
Okay.
I have the cursor moved. And I'm using focus on the telescope right now.
That looks like
That's
about as good as you're going to get.
I was going to say the same thing. Okay, let's go back and try this again. Let's turn this off. All right, we're going to go for.
Yeah, don't loop it this time though. Yeah.
All right.
Another 15.
Okay, this will be up in less than 15 seconds.
So anyway,
Theoretically.
this globular
We're getting there.
Well, thank you, Captain Obvious.
Okay, this is it. Here it comes. Whoa!
Yay, that's much better.
Yes,
there
indeed.
we are. There we are. So this is again a globular star cluster, about 450,000 stars in it, and you'll notice, a couple of weeks ago we were looking at M13, and you may recognize that this one is much more concentrated than M13. This is called a core collapse globular star cluster. The stars are much more concentrated near the center. And when we do the math, when we watch the stars as they are orbiting around the center of the cluster, and we do the math, we realize there is really a lot of mass right there at the center of this globular star cluster. So much so that there's about a 90% probability that there is an intermediate sized black hole at the center of this globular star cluster. Now, it's possible that there are black holes at the center of other globular star clusters, but this one, there's just a whole lot of evidence to suggest that that's the case here. So the stars in the cluster are orbiting around the center of the cluster. They orbit in highly elliptical orbits. So they swing in really close to the center. And when they're close to the center, they're moving very fast. And then they swing out, go way out to the periphery of the cluster. And that's when they're moving very slow. And then they swing back in and repeat over and over again. And because we can measure the velocity of the stars using Doppler techniques, we can get an idea what the mass of the globular star cluster is. So we say it has a mass of 450,000 stars. And what we're really saying is its computed mass is about 450,000 times the mass of the sun. Since we don't know what types of stars are there, and it's possible there are a lot of stars that have already reached the end of their life, and so we can't see them, the only way we can estimate the number of stars is by computing the mass of the cluster, by observing the velocity of the stars as they orbit, and then taking the total mass of the cluster and dividing it by the mass of our sun. And when we do that, we get roughly 450,000. And so we say it has 450,000 stars in it. It's entirely possible it has more or less, but that's the number we go with when we talk about these. And that's the number we go with when we're talking about all of these globular star clusters. It just gives us a way of comparing their relative sizes and the relative number of stars. Now, these stars are, I'm sorry, go ahead.
Yeah, Gerald, I was just looking closely at the image and I see a couple of blue stars. Do you think they are not part of the cluster?
Those are what we call blue stragglers. So the cluster, I was just going to say, this cluster is very old. It's more than 10 billion years old. Globular star clusters are among the first things to have formed when our galaxy was forming. So they're very old. Globular star clusters orbit in a region of the galaxy called the halo. The halo doesn't have a whole lot of stuff up there. It doesn't have all those big clouds of gas and dust like you see in the spiral arms of the galaxy. So there's not a lot of material to form new stars. So the stars that we see in the globular cluster are almost all the original stars of the globular cluster. Now, when the cluster first formed, it had high mass stars, medium mass stars, and low mass stars. All of the high mass stars have since died. High mass stars don't live very long. So in 10 billion years, they have all gone away. So what really is all is left are the low mass stars. Well, low mass stars are not very hot, so they shouldn't be bluish in color. And yet we see blue stars in the globular star cluster. And after a long time of head scratching, we realize that what's going on is those stars at the center of the cluster are so close that they sometimes bump into each other. And so they may slide by each other, and one star, a little bit more massive, will pull matter off of the other star, exposing the hotter interior. Or the two stars may collide and merge and form a new, more massive star, which then burns hotter. So that's our theory about why it is we still see blue stars in globular clusters. They are the results of collisions between lower mass stars. And again, we call them blue stragglers. All right.
Hey, Gerald, I just read an interesting fact about this. You mentioned how dense it is at the center. About half of the mass of M15 is in a sphere that's only about 10 light years in diameter from the center. So it's really, really, really bunched together at the center there.
And when you get that much mass in that small of an area, it pretty well says you got a black hole there. And it's probably a black hole that's several hundred times the mass of our sun. So we call it an intermediate black hole, intermediate size black hole.
Gerald, have they detected any X-ray sources or anything like that?
Yes.
Okay, that's a telltale fingerprint of a black hole. Is you can use X-ray detectors on that region of space, and if you're seeing a hot spot, there's a good chance there's a black hole there.
Yeah, although you can also have pulsars and things like that also producing X-rays. So, but yeah, there's a lot of strong evidence that there is a black hole at the center. Unfortunately, it's so dense there that we can't look in enough like we can do with our own, the center of our own galaxy. We can't zoom in enough to where we can actually see where the black hole is and see the stars orbiting around an empty space like we can with our own, the center of our own galaxy. All right. So
Thanks. Great
M-
description.
Okay.
Mhm.
Yes.
M15. Folks, if you got any questions, don't hesitate to post them
Don't
on
be
the chat.
shy.
Yeah.
Don't be shy.
Yeah. Otherwise, we're going to just sit here and make up stuff, you know. So, all
Yeah.
right. Well, where do we want to go from here? Maybe back towards the Ring Nebula or
Oh,
something like that?
quick question while you're moving. Another question from Renato. How do we know this cluster is 10 billion years old?
Great
That's a good one.
question.
Remember how I was telling you about how we don't see any of the high mass stars anymore? They're all low mass stars.
Mhm.
When we look at a cluster like this, we start looking at the temperatures of the stars and plotting them on a diagram called an HR diagram, which
And it doesn't mean human resources.
yeah. Yeah. So the HR diagram graphs the relative luminosity of stars against the temperature of stars. And if they were main sequence stars, they all fall on a narrow band within the HR diagram. If the stars are old, if they are no longer on the main sequence, then you would see them above the
Curve.
main sequence line, unless they are white dwarfs, in which case they would be far below the main sequence line. So if all the stars were roughly, say instead of 10 billion years old, they were 10 million years old, then we would see a lot of stars up on the high mass end of the main sequence of the HR diagram. But we don't see that. Instead, we don't see any stars up on the high mass part of the main sequence, and we see lots of stars on the low mass side of the main sequence. And so that tells us that this cluster is so old that all the high and even the medium mass stars have all left the main sequence because they've gotten so old, and the only stars that are left are the low mass stars, because low mass stars can easily last 10 billion years. Our sun is a relatively low mass star, and it's going to last 10 billion years. So that's how we know the age of this cluster.
Don't we also know that that these are old stars because of the lack of heavier materials? And by comparing the stars in a globular cluster to a star like our sun or something that is later generation, we notice a big difference, don't we?
Right. Stars that form within the spiral arms of the galaxy, where there are lots of clouds of gas and dust, those clouds of gas and dust are sprinkled with heavier metals from past supernova explosions and neutron star mergers and things like that. And so newer stars will pick up some of that heavier material, what we call metals. Anything actually heavier than helium, astronomers call metals. But you'll find a lot of carbon, you'll find iron and things like that in the stars that form from those clouds of gas and dust in the spiral arms. And when you look at the globular clusters, you don't see that. You don't see stars with a lot of heavy metals in it. And so that tells us that they had to have formed early on, before there was all that gas and dust available for them to form new stars with heavier elements in them. So it's a combination of things, but yeah, that is one of the clues. All right.
Yeah, thanks.
So
Okay.
I think we're going to the ring.
Yeah, in
The
10
ring.
seconds. In 10 seconds.
No, we're not.
Well, you guys were talking. I was imaging. So let's
Looks
see
more
what
like about
happens
15
here.
seconds.
Okay. All right. You are free
Well,
to move about the planet.
Okay.
While we're talking about that, we got a question. How long does it take to get Nellie ready for viewing use? Well, it takes about 30 minutes. We have to open up the roof and take the covers off the telescope and get the cameras attached and all that kind of stuff. So it takes about half an hour.
So I'm going to go to an intermediate point here, a star in Cygnus. And we're a little too far to the east there. So let's move the camera, not the star.
I want to see you move the star.
Yeah, I have to always keep that in mind. I got to move the camera, not the star, when I'm trying to line up things like this. All right. I think we can now go over to the ring. Here we go.
Here's a question
Little
Little V asks. Why do people say that the moon is made of cheese? Well, a long time ago, they had no idea what the moon was made of. So
It had
they
holes in it.
took wild guesses. It had holes in it. And green cheese was one of the things they came up with, and it stuck.
I always thought it was blue cheese.
Now, blue cheese would be much better.
Oh, yeah.
No, green cheese.
Limburger cheese. Okay. You want to do like a 15-second exposure or so?
Yeah, I've got a
Oh.
5-second exposure that should be coming up. Yeah, there we are. Pretty
Oh,
close.
so we got to do a little motion there, huh?
Mm-hmm. All right, let me go back to live view.
Well, we're not going to be able to see much with live view, but
Well, you got a nice start right there where the cursor is.
all
Just
right.
move that.
Yeah, I just moved
over
it a little bit. Shoot it again and see where we are.
All right. Let's give us 10 seconds on this.
So some of you are probably looking at these images and saying, well, that's not very bright. Hubble images look a lot better than that. And yeah, you're right.
Sure
There's
they would.
actually, even with a small telescope, you can get much better images if you're willing to put in the
Ooh.
time. Am I good or what?
Gerald, you are good. I think that's fine. You're happy with that? Let's
Yep.
take that off.
So
We'll go to imaging.
yeah, maybe go a little bit longer exposure.
Yeah, we'll go 30 seconds.
So, you know, you hear us taking 15-second exposures and 30-second exposures. If we wanted to make an image of the Ring Nebula or M15 or anything like that look really good, we would take lots of exposures, 30-second exposures, 1-minute exposures. Depending on how well the telescope tracks, we might go 5-minute exposures. And then we would process all those images, take the best of them, and then combine those images to form a finished product, which shows a lot more detail, a lot more color, a lot higher resolution, and so on. So we are trying to do this kind of on the fly here. So you're not getting the best, but you're getting pretty good still. So
Hey, on that topic, do you mind if I share my screen for a sec?
sure.
While you're doing that, Omar asks if this is live. Yes, we are doing this live tonight. We have clear skies and nice weather. So yeah,
So
we're doing this live.
So we're alive tonight.
We're alive.
we are alive. Yeah,
More or less.
barely, but yes.
Let me just
So-
pinch myself to make sure I'm alive. You know?
So I want to show you this image taken by one of our East Bay
Oh.
Astronomical Society club members. Molly Wakeling is really an excellent astro photographer, and she took this with an 8-inch telescope using narrowband filters. And what's interesting about this is you can see a lot of this, what you were looking at before from Rick's image, which was what, 30 seconds?
30 seconds,
30
yeah.
seconds. Basically, if you could see my cursor here, it wasn't extending much farther than my cursor. But what Molly was able to do by taking much longer exposures and over many hours and using what are called narrowband filters, which make the camera sensitive to very specific spectra of light, you were able to pretty much double the size of what you can see in the nebula using her CMOS camera and an 8-inch telescope. So I wanted to share that.
It's interesting. Do you know what filters she used?
Let me find. Let me give the. Let me give the share back to Rick, and then I'll find out for you.
Okay.
And
Okay,
come
yeah,
back in.
because I'm surprised that the outer layers of hydrogen aren't red. So I wonder whether she was using some other filter rather than an H-alpha filter.
It could be an artifact of processing too.
Yeah. Okay. All right.
Let me.
Rick,
I'll try to find out while you guys continue.
Rick,
Okay,
we got
all
a
right.
blank screen there again, Rick.
So, all right, let me stop sharing again. Actually, I've lost connection on Zoom.
Well, we still hear you, so.
Reconnecting. All right, here we are again. Okay. Now, see, this is the only way you can really tell that this is a live presentation.
Yeah,
a live
yeah.
Right.
You get to see all the boo-boos.
Yeah. Yeah.
All right, I do have the answer for you, Gerald.
Okay.
So the image was a total of 32 hours of exposure time,
man.
and 15 hours of that, so half of it was done in oxygen 3.
Ah, okay.
And the other half of it was done in hydrogen alpha. So this
Really?
is only narrowband.
Right.
So and it was done over a 4-month period.
Okay. So what she got is a lot more of the oxygen that's outside of the red perimeter in this image. You know,
That's
that
right.
red perimeter that you see in this image was actually kind of inside a much larger cloud, if you will, in Molly's image. So that red perimeter is hydrogen. It's kind of a denser layer of hydrogen. The blue-green color is that oxygen that he was talking about, what we call oxygen 3. It's a type of ionized oxygen. When you ionize an element, you strip away some of its electrons, and with oxygen 3, you've stripped away 2 of its electrons, and when you then expose oxygen 3 to ultraviolet radiation, it glows very brightly in that turquoise color that you see there. This is a star that was once like our sun. It got old, it swelled up, it became a red giant star. The red giant star began to shed its outer layers of gas, mostly hydrogen gas, but oxygen and other gases as well. That gas was slowly blown away from the star, from the red giant, over thousands, in fact, tens of thousands of years. And then eventually it exposed the inner core of the star. The star by that time had lost at least half of its mass. And the inner, much hotter core was a brighter color. And then the fusion process at the center of the star stopped. The star, whatever's left of the star, collapses, becomes a white dwarf. You can see the white dwarf right at the center of the donut hole. And it is very small, very compact, very dense. And it is emitting a lot of ultraviolet radiation, which is exciting and ionizing the surrounding gas left over from when it was a red giant. And you see it as what we call a planetary nebula. There are lots of them out there. This is a common process. It happens to nearly all stars that are 8 solar masses or smaller in size, or mass rather. And so this is what will happen to our sun in about 5 or 6 billion years.
We got a quick question in here. Let me just throw this in here while you're pausing there on these photographs. A couple of people have asked, well, don't they have to move the telescope while taking these pictures? And absolutely, yes. In fact, we're moving the telescope even for our little 30-second exposures. We're tracking the object because of the rotation of the Earth. If we didn't do that, we would lose the image in just a few seconds. So Yeah, we definitely have to track when we're doing these photographs.
If you ever get to come up and visit us here at Chabot sometime and look at this telescope, you'll see that it's on a fork mount. So I will try to show you a fork mount. So the telescope is mounted between the two arms of the fork, and that fork is slowly rotating like this. And it's rotating at the same angular rate that the Earth rotates, but it rotates in the opposite direction, because the rotation of the Earth, where we're sitting right now, we're moving towards the east. That makes the stars all appear to be moving across the sky towards the west. So by rotating the telescope toward the west at the same angular rate that the Earth is rotating, we keep the object centered in the field of view. Now, the telescope as it is right now does that pretty well. But if we were to do a 3-hour program and just look at M57, the Ring Nebula, during that whole 3 hours, you'd notice a little bit of drift of the image. That's because although it's pretty good, it's not perfect. It's not precise. And that's true of almost any telescope on any kind of a mount. So what a lot of astrophotographers do, and I'm sure Molly is one of them, they put a second smaller telescope on the main telescope. They put a special kind of camera on that smaller telescope, and they do what's called auto guiding. And with that smaller telescope and smaller camera, they pick a star in the field of view of that small telescope. And then they have software that you tell it, keep that star over the same set of pixels in the camera all the time. And so the software is sending signals to the mount to make slight, very tiny adjustments to the tracking of the mount to keep the guide star, we call it, the guide star, right in the same position in the field of view of the camera on the small telescope. And by doing that, they keep the main telescope precisely pointed at the target. And that's called auto guiding, and it's a very common practice by astronomers at almost all levels of expertise.
Okay.
Did I explain
All right.
that well?
Perfectly.
That was perfect.
Absolutely.
I have like nothing to add. And,
Yeah.
and you are exactly right. Of course, Molly does use a guide scope and a lodestar guide camera.
Is that what she uses? Yeah.
I do.
All right.
Same one I use.
Okay, well, where should we go from here?
I think it's planet time.
Yeah.
Oh, yeah. Those are up, aren't they?
They
Got
are.
our two
Okay.
largest
And
planets.
I think we ought to go to Jupiter because we might be able to see the GRS.
Oh, well,
yeah, it's getting late.
okay.
Let's see.
All right. I'm going to head on down to, where should I go? I think I'll go to Enif first. So go to live view, Rick.
We're in live view. Yes,
All
we
right.
are.
All right. We'll head over to Enif. Oh, yeah, there it is. Oh,
Yeah, we still have the great red spot near the center. So if we have good
Yep.
viewing,
all right.
should be able to see it.
Hang on just a second while I correct this a little bit here. Boy, it's not very responsive.
Are you stepping on the wire over there?
Just seems to be not very responsive. Okay.
Well,
You're not doing a looping, are you?
No,
Oh, okay. All right. Well,
no, this is live view.
all right.
Blame it on the cameraman. There
That's
we go.
right.
That's
Right.
right.
We always get it.
Telescope operator knows what he's doing. It's got to be the cameraman.
Well, it's either that or I blame it on the computer, one or the other.
Yeah, well, yeah.
Yeah.
I was
You can
about to
always
say,
blame it on the
there are-
computer.
There are
Yeah.
several
All right, here we
computers
go.
involved.
Okay. That's better.
There it
Whoa. Okay.
is.
Ah, blah.
All righty.
I think we need to do some adjusting. I can see some moons really well.
Yeah, we see. Yeah,
Let's
get
see
a
what we
load of
can-
those moons.
Yeah, the two right next to each other are Ganymede and Europa. On the other side is Io, and then way out on the other side, out of range, is Callisto.
This is the same configuration they were in last week when we did this.
No, Callisto was out farther to the left last
To
week.
the left? Oh, okay.
Yeah, this time it's out to the right,
All right.
but it's so far out, it's away out of the field of view.
Yeah. This.
So anyway, this is Jupiter and 3 of its 4 Galilean moons. Which one is the closer in Europa or?
Io is the one on the right side, in
Oh,
close. On the other side, yeah, Europa is closer, and then Ganymede.
Okay. So Io is kind of interesting. Io is the closest of the 4 Galilean moons. It takes just under 2 days to make an orbit around Jupiter. So it moves very fast. So even in the course of, say, observing Jupiter for an hour, you notice a significant amount of movement of Io. And you notice that all the moons appear to be lined up. That's because the plane of the orbits of the moons are all more or less on the same plane. And that plane is aligned parallel to our line of sight. And we're going to have an argument now about what is parallel, perpendicular.
No, you're right. It's parallel.
Okay.
The way you said it.
All right. The plane of the orbit is parallel to our line of sight. So as the moons orbit around Jupiter, we don't see them moving in a circle around Jupiter. We don't see it that way from Earth. It appears that they just move back and forth, moving across Jupiter. And when they happen to pass in front of Jupiter, they can cast a shadow on Jupiter. And often we're able to see that shadow. So it can be pretty interesting at times. Now, there are many more moons. I think we're up to 79 moons around Jupiter. But most of them are very small, only a couple of kilometers in diameter. So we can't see them from here on Earth. But the 4 Galilean moons are pretty big. 2 of them are actually bigger than our moon. And one of them, Ganymede, is the largest moon in the solar system. It's actually larger than the planet Mercury.
Rick said it's like a 60th of a second.
Yeah, it's giving me some issues here again.
Jerry, in the meantime, Jerry asks if Jupiter was the first bright object he saw tonight in the east. Well, I don't know exactly where you were looking, Jerry, but
most
probably
likely
was.
Yeah, most likely.
It's the very bright object that was that came up in the east earlier.
And if you look to the right of Jupiter, that bright object, if you put your hand out, hold it out at arm's length, spread your fingers, sort of not completely, but about halfway, and then hold it up and put your thumb on Jupiter, your middle finger, assuming you're doing this with your right hand, would be on the planet Saturn, which is fainter than Jupiter.
Yeah, you got to scroll down. There you go. Yeah.
Now, if you want to get a really good image of Jupiter, this is not the way to do it. The way to do it is to put a video camera on the telescope and shoot a couple of minutes worth of video, and then go through it frame by frame, picking out the best images, and then stack those together. And that can give you very good images of Jupiter. In fact, I think last week, Rick, didn't you, or Rich, did you show us a Damian Peach image?
Yeah, it was amazing.
Yeah.
They're kind of busy working on the computer at the moment. So
Are you? So what are we doing here? I'm running out of things to say. They're really
No,
cool.
we have an interesting question here. Mark asks, are we ever able to detect lightning storms or aurora activity with large telescopes on Earth or HST, or are those only detected by spacecraft like Voyager? I think you have to be close enough to the planet.
Yeah, I actually
see
think
those.
the Hubble Space Telescope has seen some aurora on Jupiter. I don't know about lightning though, but yes, spacecraft orbiting Jupiter. Right now, we have a spacecraft called Juno that's orbiting Jupiter, and those can definitely see auroras and lightning in the clouds. Jupiter is a gas giant. It's a big, huge cloud of gas and dust. Or I'm sorry, not a cloud, a big, huge planet of gas. The gas gets denser and denser as you get closer to the center of the planet. We actually think it may have a solid core. And it is turning very rapidly. A day on Jupiter averages about 9 hours and 50 minutes. So you got a planet that's 11.2 times the diameter of the Earth. So it's way bigger than the Earth, but it's turning around its axis once every 9 hours and 50 minutes. So less than half the time it takes the Earth to rotate once on its axis. So because of that, the winds, especially near the equator, can be moving very rapidly. And if you get high and low pressure areas in the atmosphere of Jupiter, instead of forming little spirals like we see on Earth, the high and low pressure areas just wrap themselves all the way around the planet, forming dark and light colored bands. And if these guys ever figure out what they're doing,
We did. We figured it out.
right,
We can prove it to you. Rick will share his screen in a second.
Hey, Little V asks, did Jupiter explode? No, it's still there. I'm not sure what she meant by that, but it formed when the other planets formed. It's the largest planet in the solar system.
oh, there we go.
I don't think it ever exploded.
So in order to see the bands, we have to kind of lower the exposure so much that we don't see the moons anymore. But you can see some dark and light colored bands. If we had a little bit higher resolution, we could see even more dark bands wrapping around it.
We gotta try brightening it up too.
Yeah.
To increase the ISO or the exposure time, either one. Yeah.
Did you say that the GRS was?
Yes, it's there. You can see it. It's about at the 4 o'clock position.
Oh, okay.
On the
yeah,
lower
all
band.
Right. Yep.
Yeah.
I see
Yep,
it
right
right
there.
there.
Yep,
Right
yep.
there. Right there. Yeah. So that's the great red spot, which is not so red these days.
And not so clear in this image, but
yeah.
we'll try to.
Well, you could try
it
playing
better.
with the contrast and brightness settings to get those up. Yeah.
Yeah, you can sort of see it there.
Too
Yeah, I
much.
don't think
Right there.
too
Right
much.
There we
there.
go, right
That's
there.
good.
Oh,
Oh,
there it
wow.
is.
Yeah,
There it was.
You hit it a
Yeah,
little bit better.
but we don't see it.
I'm seeing it. Looks good to me.
you had it a little better there.
You
a
had
minute
it
ago.
better a second ago. Now you need to adjust. I think it was the brightness setting, not the stacking.
Well,
there we go.
Yeah, right there.
Right. Yeah, that's.
A little bit better. Yeah. Contrast maybe a little bit more too.
Yeah.
Ooh.
Stop.
Yeah,
Stop. Perfect.
Yeah, I'd almost go back a little bit, but not much.
Oh, look at
There.
it coming out. Yeah.
Yeah.
All
Leave
right.
it alone.
Yeah.
Leave it alone.
Okay. Let me fine tune it. Woo.
It's not Pix Insight.
Okay.
All right.
More like
so-
on television, they can always sharpen these
This
things.
is
up.
more like driving a motorcycle.
Yeah.
Yeah, I need my sharpening filter. That would
Right.
work. Yeah.
One of the things you're going to notice is that it gets a little sharper periodically, and that's because of our atmosphere here on Earth. We are shooting through a whole lot of air, and air currents up there because of winds, upper level winds and so on, change the density of our air from moment to moment. And that slightly alters the image and makes it sometimes look a little sharper, sometimes a little blurrier. There's not a whole lot we can do about that. And that's one of the reasons why, I was describing earlier about shooting video. When you shoot video, you take a whole bunch of frames in a very short period of time. Some of those frames will be shot when the air is nice and clear. A lot of them will be shot when the air is kind of fuzzy. And so by picking through them, picking only the really sharp ones and then stacking those together, you get a really great image of Jupiter. And Rich, you had shown us a nice example of that last week, I think, from Damian Peach. Somebody get Rich to sit down and stay put.
Yeah, sorry. I was being interrupted.
Tie him to that chair.
I keep talking to an empty screen.
What makes you think we're listening to you?
Yeah, I'm sorry, Gerald. Did you say something?
Yeah, okay. All right,
Gerald, here's a question for you if you want to have something to say.
We're not married, so you guys don't have excuses.
So Colin asks, Nelly is a research grade scope. What kind of research is done on it?
Oh, gosh.
Oh, you got him started now.
Yeah,
Okay. Hey, guys, we can take a break while Gerald takes it.
You guys are so... We look for asteroids. That's all I'm going to say.
You're able to answer.
There you go. That was a short answer.
You answer the question. We will let you answer the question.
All right. So Nelly is part of a global network of observatories that searches for and tracks near-Earth asteroids. There are about 1,000 new near-Earth asteroids that are discovered every year, and when they are first discovered, we need to make a lot of observations of them and track them for a period of time, and so we can compute their orbits and figure out how big they are, and maybe find out whether or not they are a threat to the Earth. So that's what we do with this telescope here. That is our primary research project. Just spend lots of time taking images of star fields and looking for stars that move. The word asteroid means star-like. And when we do this, the asteroids do look like stars, except if you take one picture of a star field and then you wait 10 or 15 minutes and then take another picture. If there's an asteroid there, one of those stars will have shifted position. And so that's how we do it. So that's the research we do. We were discussing last week, we met with one of the folks from UC Berkeley talking about another potential research project that we might do where we measure velocities of asteroids and maybe some other things using a Doppler technique. But that still remains to be seen. There's a lot of work that needs to be done. Plus, I think he needs to get some more funding too, as I recall.
He's got the funding. He just needs to find a lab.
Oh, okay.
So I always like seeing people ask about the James Webb telescope. We do have a question about James Webb. Michelle was mentioning that it's being launched. It's not being launched from California, Michelle. It's being launched from French Guiana, which is in South America. It's been in California for many years, and it's being put on a ship that's going to go through the Panama Canal, and it's going to go all the way to French Guiana and unloaded and integrated there with the rocket. It'll be in an Ariane rocket, and then it will be launched to its location in Lagrange 2, which is very far away. It's about 5 or 6 times the distance of the moon. But even if it was being launched from California, it wouldn't really affect our viewing because launches are pretty quick events, right? 10 minutes, they're over. So it really doesn't have an effect unless it's like right overhead. So if they were going to launch the James Webb Telescope from Chabot, I would say it would affect our viewing.
Yeah,
But we wouldn't care because we'd be watching a rocket launch from Chabot.
right. That would be more fun anyway.
Yeah, that's right. Good question, though. Thank you.
We got to have our priorities straight. Yeah, and we're hoping that the Ariane rocket will perform better than the Astra and Firefly rockets did earlier this
Yes,
week.
the sideways moving rocket.
Yeah. Unfortunately,
Yeah.
two startup companies, one of which is based here in Alameda, both of them attempted to do launches within the last few days, and both of them failed. One never really got off the launch pad. The other one got off the launch pad, but then started having problems in flight, and they had to destroy it. So, it ain't easy getting to space. So takes a lot of expertise and a lot of careful planning and well-designed equipment. And even then, you're still crossing your fingers a little bit.
Well, it's 10 o'clock. Should we have a quick look at Saturn before we stop?
Oh, yeah.
Yeah, why not? Let's do that.
Good idea. Somebody needs to have their muffler fixed.
Yeah, I think so.
Well, either that or they just had their catalytic converter sawed off.
Maybe.
One or the other.
Don't say that, Rich.
Yeah, that's sore subject here.
That happened to a bunch of cars up here a few weeks ago. So.
Oh gosh, I didn't know that. It is a tradition here in Oakland.
It's
glad you can.
It's a situation.
Consider it a tradition. Huh?
Yeah.
Okay, well, I think we're there. The software says we're here.
Oh, and there's Saturn.
There it is. Let me tweak the positioning a little bit. That's actually a pretty good view.
Oh, that looks great. Look at that.
Oh.
Yeah, that is a pretty good view. Well, it's nice to not have to deal with the smoke.
Yeah, it is.
All right. So there is Saturn, the ringed planet, aka the Lord of the Rings. Let's see if I can tweak the focus a little bit here. I'm either going to make it better or I'm going to make it worse. That's a little better. Except, what did you do?
Oh, I'm fixing it.
Well, stop fixing it.
It wasn't broke. It wasn't broke.
Right. All right. Let's try
so that's a nice view right there.
Given the opportunity to press buttons and move sliders, we're gonna do it.
That's actually a pretty nice view there. You can actually see some of the banding on the planet itself.
Yeah, it looks good.
That's excellent.
And you can just barely make out the Cassini division in the rings. So nice view.
You can see a little of the planet shadow on the rings too.
Yeah, on the left side.
On the left side, yeah.
Yep.
Wow.
Yep.
I'm trying to get the right exposure dialed in here.
I think you got it.
We're getting there. Everyone's a critic. I can't believe it. Okay. Well, I can't see Cassini, but there we go.
Well, yeah, I'm not surprised. In order to get a proper exposure of Saturn, you kind of underexpose the moon Titan. But still, that looks pretty good. Saturn is another one of those gas giant planets. It's 9.5 times farther from the sun than the Earth is, and it's about 9.5 times the diameter of the Earth. A day on Saturn is a little bit longer than on Jupiter. It's about 10.5 hours long. And its atmosphere doesn't have quite as much variation in color. It's just various shades of tan and yellow, pale, very pale yellow. And, it's just, of course, everybody who doesn't look at the bands on the planet, they all want to look at the rings, right? The rings are composed of ice. You can't resist it.
No. now, if the adjustment had worked, you would have said, "Hey, great job!" But such is life. We keep trying.
What do you mean by worked?
Well, I was trying a stacking technique on it, but it didn't really lend itself to that.
All right. So anyway, the rings are made out of ice, chunks of ice, most of which are about the size of your fist. There are a few bigger pieces of ice in there. And there's different theories about how they formed, theories about captured asteroids that broke up, or old icy moons that got too close to Saturn and broke up. Different theories about it. And also there are some theories that say they won't last forever, that if you come back in a million years, they won't be there. So I guess we are the privileged few who get to see the rings. And that's actually going to be true for several hundred or thousands of years yet. But it's very thin. The average thickness of the rings is only a few tens of meters at the most. There are some places where it's thicker, where it's being disrupted by little tiny moonlets that are embedded within the rings. But for the most part, the ring plane is very thin and lots of ice. And if you did a close-up, I don't think we'll do it tonight, but maybe next week we can do it. I'll show you some close-up images of the rings, and you can see that what looks like just 2 rings or maybe 3 rings in this image are actually hundreds and hundreds of much smaller rings that are all just kind of one right after the other as you move out from the planet. The way orbital mechanics works, the ice particles that are orbiting closest to the planet orbit faster than the ice particles that orbit farther away from the planet. And as a result, you get sort of clustering within the rings. So you get little ringlets. And it's a pretty neat image when you can actually see it close up. We had a spacecraft called Cassini that orbited for 11 years, and it gave us a lot of really good imagery of the ring. So maybe we can share that next week.
Yeah.
Maria asks, how many moons does Saturn have? And I think the current count is 82.
Is it really?
That's what I just looked up. Yeah.
No. Well, so the answer is maybe 82.
Right.
And maybe more.
A lot of really tiny ones.
Yeah, they're all very small. In fact, so much so that we kind of, astronomers kind of got into a little bit of debate about when do we stop calling it a moon and just call it a rock in orbit around
right.
Saturn. And they've kind of set the limit at 1 kilometer. So if it's bigger than 1 kilometer, they'll call it a moon. If it's smaller, it's just a rock or an asteroid or something like that. Okay.
What do you think, guys? Is that going to do it?
I think that'll do it, unless we have any other questions, burning questions. If you need to ask questions, now's the time. Anything about the planets? Or
Let's see if we can see some of the moons.
don't see it that way.
No, I don't see it that way.
Yeah, there's one moon. The moon Titan is a very big moon. It's one of the biggest moons in our solar system.
Yeah, it's out a ways, but you should be able to see it in that size image. But
yeah,
you have to. I think you need to.
Well, if we
get your exposure up,
we'd have to get the exposure up, but it's going to totally. Well, there they are. Okay. There's a couple of them. Let's go a little more.
Yeah, the one in the upper left there, the bright one is Titan.
Yeah, there you go.
Rhea down to the lower left. And Dione out to the right.
Frank on YouTube says he was just at Yosemite and was looking at Saturn with his 8-inch telescope, and the sky was so clear, other people would come up and look through the telescope and accuse him of having a movie in his telescope.
That's happened to me before.
Yeah,
too.
we get that a lot.
Yeah.
Oh, that's just a slide you put in
There's
there.
a slide in there somewhere. Yeah. Like, where are you even going to find a slide anymore?
All right. Well, thank you,
Okay.
everybody. We appreciate you staying with us here as we work through our glitches. And we want to remind everybody that Chabot Space and Science Center is still closed to the public, although we are doing rental events. You may have heard it in the background. There's one going on right now. And we will be opening again in November. And in the meantime, we are doing lots of refurbishing of the interior of the facility. We do have staff here during the week who are working on new programming, developing new everything from a new brand to new training materials and so forth, and also producing additional virtual programming. So we do continue to need your support. So if you can take a moment to click on that donate button on Facebook, if you're on Facebook. If not, you can go to the Chabot Space and Science Center webspace, our website. It's chabotspace.org. And when you get there, you'll see a donate button at the top of the page. You can click on that, or you can go to the membership page and sign up and be a member. And there will be a lot of upcoming events once we reopen that are members only type events. So you don't want to miss out on that. So help us out in whatever way you can. We really appreciate it.
Sure do.
All right. Well, good
Okay.
night. I hope you all join us
Alrighty.
again next week.
All right.
Yeah.
All right. So we'll
Good night,
sign off.